Good morning, everyone. We are going to learn about the energy level diagrams for molecular orbitals. We have already discussed about molecular orbitals. Now you must be knowing that, yes, that atomic orbitals, when they are combining, they are forming molecular orbitals. Also, I told you that when two atomic orbitals are combining, we get two molecular orbitals. One is bonding molecular orbital, BMO, and the other one is anti-bonding molecular orbital, that is ABMO. These are the short forms. Now see, I have just listed out a chart which you will be seeing in the later part, the molecular orbitals. Left hand side we have all atomic orbitals, right hand side we have all molecular orbitals. Now see, when two atoms with 1s orbitals, atomic orbitals, combines, we get two molecular orbitals. One is sigma 1s, the other one is sigma star 1s. The asterisk mark one, that is ABMO, that is anti-bonding molecular orbital. The other one is bonding molecular orbital. Similarly, when two 2s combines, atomic orbital combines, we get again two of the 2s molecular orbitals. One is sigma 2s, which is BMO. The other one is sigma star 2s, which is ABMO. Similarly, we have three p orbitals, px, py, and pz. How do they combine? Pz, two of the two pz's, if they combines, you have again sigma 2pz, that is your BMO, and the sigma star 2pz, that is your ABMO. Now when two atoms are there where your 2px orbitals of those two atoms combines, then what happens? We form pi orbitals. One is pi 2px, that is your BMO, and pi asterisk mark 2px, that is your ABMO. Similarly, when the atomic orbitals, that is the py orbitals, are combining, we again have pi molecular orbitals. One is simply pi 2py, which is your BMO. The other one is pi star, that is asterisk mark 2py, which is a ABMO. Now, the points which you have to remember again is, see, just in the case of atomic orbitals, what you have seen is, you just have seen that, yes, when the energy shell, that is a quantum number, principal quantum number, when it is less, then less is its energy. So we have already known that, yes, 1s atomic orbital is having less energy than 2s. Okay, quantum number increases, the energy of that orbital also increases. Similarly, in this case, in the case of molecular orbital also, you will be seeing the similar case. Sigma 1s molecular orbital will be having less energy, of course, than sigma 2s. Now, if we have the same quantum number, that is the same shell, here it is in the case of molecular orbital, you have sigma 2s as well as you have sigma star 2s. So in that case, previous day we have already discussed that the bonding molecular orbital will have less energy than the anti-bonding one. In the same shell, this happens. Third point, you have to remember that when we talk about the px and py, here in this case we have degenerate orbitals. Degenerate orbitals. Degenerate orbitals means the orbitals which have the same energy. So in that case, you will be seeing that pi 2px, this is x, pi 2px will be equal in energy with pi 2py. Similarly, pi star 2px will be similar in energy with pi star 2py. Okay, these things you will be seeing. Now we move to the later part and we just draw the energy level diagrams. So this is the thing. See, for lithium, beryllium, boron, carbon and nitrogen, we have the following energy level diagram. Now the first thing is, you just noted there that you have sigma 1s, then you have sigma star 1s, okay, then 2s, sigma star 2s. Then you have pi 2px equals to pi 2py, and higher that 2pz is your higher in energy. This one is higher in energy. There is a reason for that. Because in these this molecules, what happens is, this, like for lithium, beryllium, boron, carbon, nitrogen, in this cases 2s and 2p orbitals, those orbitals have slight energy difference. So due to the slight energy difference, what happens is repulsive interactions comes into play, due to which sigma 2pz is raised in energy. So this part comes before sigma 2pz. Okay. Then as usual, the asterisk 2px, 2py are there, and at last always sigma star 2pz you will be finding. So in your syllabus, what about the sigma and the pi's, you will be finding that molecular orbital with sigma star 2pz, that is the antibonding one, that is the higher one, highest in energy. Now this is the energy level diagram where you are seeing the similar ones arrangement. What I have written here, the similar ones arrangement. Now of course you can understand that this is the energy going higher. Okay, this is the upwards, the energy is going higher. Now similarly you can just see these are the atomic orbitals. Please understand, this is one of the atomic orbital, this is another atomic orbital. These two combines to form one BMO, and this is one ABMO. Similar is all the cases, the upper one also. Okay, so I'm not discussing it. Now let us take an example. Let us take the example of N2. How do we draw the molecular energy level diagrams? See, for N2, we know that nitrogen's electronic configuration, if you see, what's that? 1s2, 2s2, and it is 2p3. Okay, each nitrogen is having 7 electrons, so that is the electronic configuration arrangement. Now, total number of electrons we will get from 2 atoms of nitrogen is 7 plus 7 equals to 14. Okay, now what happens? You have to arrange this 14 electrons in this molecular orbitals. So let's start with that. First, I'll go on doing with only the molecular orbitals, that's the middle part. Okay. Later, we'll adjust with the atomic orbital. You can do in both in ways. First, I'll start with this. Okay. If you start doing this, again, another thing that you have to remember here is what I have asked you already. I have asked you, that is, you have to fill the molecular orbitals with electrons, maintaining the Aufbau principle. Okay, now Pauli exclusion principle and also the Hund's rule. Aufbau principle, what we know, we are filling the molecular orbitals already, we are filling in the increasing order of their energy. It's arranged already, so that is fine. Now Pauli's exclusion principle is that maximum number of electrons which can be accommodated in a molecular orbital will be 2. As we have seen in the case of atomic orbitals, similar is in the case of molecular orbitals. It's 2. Each box will have 2 electrons. Okay. Next, the other thing is, the third one, which this will follow, is Hund's rule. Now for that, if 2 molecular orbitals are there, which are having the same energy, then electrons will be singly, it will occupy, and then it will occupy another electron. So let's check with that. Already Aufbau principle, with that we have arranged the energy level already. Okay, let's start with the 14 electrons. So this is the lower, so it will get 2 over here. Done, 2. Next, 3, 4, 5, 6, 7, 8. Okay, 9, 10. This is Hund's principle, Hund's rule, that as we can see the 2 boxes in equal energy, so you have to first singly filled up, then we have to we can give another electron. Okay, so how many were there? 5, 6, 7, 8, 9, 10. 10 already there. 11, 12. Filled, completely filled. Then we can go on the top. 13, 14. So this is our arrangement. Okay. Now we can just fill it in this way that your 1s atomic orbitals. See, here you have 2 atomic orbitals. Of course, 2. Here 2. See, for nitrogen we have written, no, here 1s2. So each nitrogen, suppose this is one nitrogen atom, this is one nitrogen atom. So each will have 2 electrons. So this is 2 electrons I have drawn for both of them. Okay. 2s2. So here 2 and here 2. Then 2p3. So here this is one nitrogen atom, this is one nitrogen atom. So 3, right? So how will you put it? It is singly filled first. So this is singly filled. Okay, so done. That is the way we are doing. Now by doing this, what we can understand, or what is the significance of doing this energy level diagrams is, we can find the bond order from there. Bond order here is number of electrons in the bonding orbitals minus number of electrons in the anti-bonding orbital divided by 2. So let's check the bond order here. See, we just have to calculate number of electrons in the bonding orbitals. How many are there? This is my bonding orbital. This one is the bonding orbital. 2, 4. Okay. These are also bonding. 5, 6, 7, 8, 9, 10. 10 minus anti-bonding orbital. How many we have? The asterisk ones. This is 2. This is 4. Okay, only 4 we have. So 4 divided by 2. So in that way, what we are having? 6 by 2 equals to 3. So bond order is 3. That directly means that between nitrogen and nitrogen atom you have triple bond. Okay. Now in cases where you'll have Nb is greater than Na, that is number of electrons in the bonding orbital you will be finding more than anti-bonding ones, then it is a stable one. It's a stable one. Stable. The molecule is stable. Also, the bond order can be in fractions even. It can be 1.5, it can be 2.5, and that is not for molecules, that is for ions. So less stable, of course, than the molecules, but it can exist. Now, if the reverse happens, Na is less than Nb, then it is unstable. Unstable. Even if it is Na equals to Nb, both are equal, then also it is unstable. Okay. Now let us go for the next energy level diagram. That is this one. For oxygen and fluorine, also neon is there, we have the similar arrangement of the energy levels of the molecular orbitals, but there is a slight difference here where we can see that sigma 2pz comes before this pi 2px equals to pi 2py, which was unlike that one. This was sigma 2pz was having more energy than the pi orbitals there in those cases, those molecules. So in this case, it is so because s and p orbitals have a considerable less energy difference, so there is less the repulsive interactions, and hence this arrangement we can see for these molecules, oxygen, fluorine, and neon. Okay. Now let us check for oxygen molecule here. One of that I will check. Okay. For oxygen, see how do we write oxygen? 1s2, 2s2, 2p4. This is our arrangement. Okay. So 2 oxygen atoms are there. So this part, left hand part is our one of the oxygen atoms. Right hand part is our one of the oxygen atoms. Middle ones are the molecular orbitals. Now let us go for that. Oxygen plus oxygen. So I'll get 16 electrons in total. Okay. So let us arrange that with 2, 2, 2, over here 2. So how many? 8, 9, 10. Okay. Now this 2 will be 14 then, and 15 and 16. So this is our arrangement. We will do it here also. Middle ones will do molecular orbitals first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14, 15, 16. That's our arrangement. Now when we do the calculation for bond order, we have to calculate the number of bonding electrons. So that is Nb minus Na, as I told you, divided by 2. So Nb, how many are there? Over this one, Nb 2, 4, 5, 6, 7, 8, 9, 10, right? So 10 minus antibonding ones. Antibonding is 2, 4, and we have 5, 6. We have 6 divided by 2. So 4 divided by 2, we have 2. So that is why it is oxygen, double bond oxygen. Okay, so doubly bonded. Fine. Also, we can check the paramagnetic or diamagnetic characters from here. We just have to see the unpaired electrons. If any unpaired electrons are left, then it is paramagnetic. Otherwise, it is diamagnetic. Do you see any of the electron left out unpaired? Of course, all of them are paired. Till here, all of them are paired. But here you can see the unpaired ones. So that explains correctly that oxygen is a paramagnetic one. Okay, it's a paramagnetic molecule. Okay, now if that was a case of iron, where you can see, suppose I don't have space here, but here I'll write O2 minus if it was this iron. Then what would we have done? Already it is 16 plus, because of this minus means 1 electron is more, so 1 equals to 17 electron would be there. Okay, 17 electron. So that the 17th electron, 16 electrons are already there, 17th electron would come here in this case. Okay, here. Okay, pairing starts. So in that way, now again number of Nb minus Na you have to do. Nb minus Na divided by 2. Okay, what would be coming? Already in the bonding orbitals we have got 10. So minus, now antibonding 1 electron will be more. So 7 divided by 2, that is 1.5, you'll get the bond order. Okay, so in that way you may have to arrange the bond orders, or they'll ask you the bond dissociation energy or the stability of the molecule. Suppose they'll give O2 minus ion and O2 molecule. Okay, which is more stable? O2 minus, we are seeing that bond order is 1.5. But for O2 we are seeing that it is 3. Bond order is 3 means it is more stable. Higher the bond order, more stable it is the molecule. And bond dissociation energy, that is the energy required to break a bond, will be just inversely proportional to the bond order. Sorry, directly proportional to the bond order. Because if bond order increases more than bond, more you require energy. Bond dissociation energy will be higher. So to break O2 molecule into its individual atoms, we require more energy than that O2 minus ion, because its bond order is less. Okay, so what did I tell you? Bond order, I'll write it over here. Bond order is directly proportional to bond dissociation energy. Okay, you have to remember that. And they'll ask you whether the molecule or the ion is paramagnetic or diamagnetic. That you can see. Bond order they'll ask. In that way they'll ask. Okay, now I'll give you something to do it. You just solve. You try to solve it. Okay, just remember the energy level diagrams. If you want, you can go through the video once again. Okay, the previous one also, the previous video also, in class you are going through it. Also you can check later also, no? If any doubt arises, you can ask. Okay.